Okay, here we go. So next is I need a haircut. Welcome to Air Science. Um, Fronts. So this is going to be something you are experiencing today. I don't know if you play with any weather apps or not, but if you want one that has pretty easy, slick interface, not a ton of like ads or trying to bug you to buy anything. WHAM, which is the one of the news networks in Rochester. And Rochester weather might actually be better for us because it comes up the lake versus Syracuse. Because things tend to come across. Syracuse weather sometimes doesn't necessarily pay attention to us up here in the North Country, but the Rochester one might be a little bit better. So give it a check out, WHAM. And if you do, a thunderstorm warning just popped up, and the radar is very like it's this is their web version, but the radar is pretty good too. So what we can see up here would be that low pressure system from the last video, and as cold air is like swooping down from Canada over Michigan and through the Ohio Valley over here, see that line right there of thunderstorms? That's a clear signal of a cold front to meteorologists. And we zoom out a touch more. We've got a warning going pretty late tonight, so I don't know if some of these other ones will develop as any of these swing across. Um, we'll get those thunderstorms associated with the cold front. So we'll see. Keep an eye out the window while we're doing these notes. So let's see. What are we going to do? Here we go. So if we're talking fronts, it is the leading edge of an air mass. Remember those? We mentioned in the last video. And again, they're right in the reference tables. So find your reference table. That's them right there. Continental for dry, maritime for wet, Arctic for frigid, polar for cold, and tropical for warm. All right, so we won't go and rewrite all of those, but those are the symbols. And again, those symbols are right there in the reference table too. So, hey, I forgot those. There they are. They're sitting right there. The station model thing we're going to figure out in another video. So we're going to spend a lot of time looking at these fronts. I don't know. We're not going to worry about any of these, but they tend to be the place where weather events take place because it's like an automatic instability when you have a front kicking through. So if we, from the last notes, borrow the idea that maybe there's a low pressure system up here, what's going to happen? Let's even do the right colors. Is that we'll have a cold front. And this is what's going on right now, if you're watching this today. Cold fronts coming on down, bringing this continental, polar, cold, dry air down from Canada. Once that fully sweeps over us, we're going to expect it to be cooler and drier, which it will be tomorrow. Because right now we are sitting in the last little bit that hasn't quite gotten swept out yet of this warm, wet air that's coming up from the Gulf of Mexico, maritime, tropical. Okay. Now, we've kind of mentioned this already in the other notes, but what we really got to get into on this one is just like with the high and low pressure systems, that's great if this were a two-dimensional map, but we know that the atmosphere is three-dimensional, so we got to be able to see these things from the side. So what does a cold front really look like from the side? If this is the ground, and again, inside view, so like this is somebody's house, only that's gigantically oversized, but it just helps people picture, even if my scale is wrong, it helps people picture what's going on here. So what we've got is behind it, continental polar, cold dry, air moving forward across the surface. Now where it contacts the ground, let's say right here, that's what a meteorologist labels as on the map, that's what they're going to call the front. Where does that leading edge of cold air touch the ground? Okay. That's really implied in this diagram up here already. What we're going to do now is say, okay, great, but what happens above the surface? This diagram doesn't take into account that there's a thick atmosphere, thick atmosphere sitting above Earth's surface. What happens? Cold air is more dense. Going way back to density, like one of the second or third labs that we did. Things that are more dense sink, things that are less dense float. So since cold air is more dense, it can't come up over top of the warmer air it's replacing. It's got to like jam its way underneath. So what happens is that you get this kind of steep edge to it, and this air is plowing forward underneath the warmer air over on this side, underneath the wetter, warmer air, maritime tropical. So this maritime tropical air has no choice but to rise up. And this is these are quick, like violent things. The cold front systems are all about like, boom, things are fast, things are violent. We get our big storms through this. This would be how you develop the supercell storms that are big enough to make large tornadoes out in the Midwest, or our decent summertime thunderstorms that we have here. And what I'd have to do, and I think I closed it, I don't want to rewrite it all because we just did it in the last notes, and this diagram is way tinier. Not that I can't make it bigger. But we got the same thing happening. Air rises. So if you go through that whole list, air rises. So it expands and cools. It hits the dew point. The relative humidity is 100%. Condensation occurs, which forms clouds. That all happens here, just like we wrote on the last set of notes. It's still rising air. Last time, yes, the rising air was because of a low pressure system. This time, the rising air is due to a cold front, but that doesn't change the idea that it's rising air, and that rising air leads to clouds. The thing that makes cold front ones unique is that they are very tall clouds. Because this is such a violent, abrupt rising air situation, you get very tall clouds. This is the tallest clouds in nature. And they have an anvil shape is the classic name of what we call these. Anvils are like those big metal things in Looney Tunes that they drop on each other's head, like a blacksmith does their work with them. Anvil-shaped clouds that then they're so tall that there's a lot of up and down action in here. That's what can create the static electricity enough to have bolts of lightning, which is why there's thunder. And it all happens like in a quick, violent situation. So like that thunderstorm this morning at like 7:30, whenever it was, right when I was coming to school, that whole thing was over in like 20 minutes. It blew in, was violent, windy, wind shifts, lightning, big dump of rain, but then was gone. Then it moved out, right? That's very, very, very textbook typical of a cold front. And again, according to my warning, there may be another one today. So keep an eye out for that. Okay. All right. So that diagram, I think, is actually on these notes. There's how the regions would draw it. And we'll talk about these questions in a minute. But these diagrams absolutely can show up. How are warm fronts different? Let's do the same situation here. Here's the ground. Only now we're going to say, what would it have been like? What would it have been like as this warm front approached us? If I had done these notes a couple of days ago, right? So in that case, we had maritime tropical air on its way into town. It's moving forward. So it's warmer and wetter, both of which make it less dense. So less dense air. And that wet air is less dense than dry air, which is going to always feels intuitively backwards. Because you think of like, if I hold a jug of water here, water's heavy, right? But in its vapor form, the way that it displaces other air, wet air is actually less dense. So we've got this less dense air that's going to come at, let's say, just cooler, drier air most likely, but we can just stick with cooler. So cooler air is over here. Well, it's cooler, so it's more dense. So this air can't go underneath. That doesn't work. What it's going to do is rise up. And kind of these things are nice and polite and gentle. They just kind of slowly rise up and say, cooler air, you can go ahead and move along now. They move slower. There's not that like forceful, like, kind of like thing happening. It just like rises up and pinches that cooler air out of the way. Is air rising? Yeah. So does it expand and cool and all of that stuff? Yes, absolutely. We're still going to get clouds. Only now, since it's not rising so quickly, it rises a lot more. I should make these clouds a different color. It's rising a lot more slowly. What you end up getting are like flatter, wider, broader clouds, stratus clouds. I don't know if I named this. This is a cumulonimbus. These would be a series of stratus clouds, strata, sheet-like, that kind of idea. You can get if there's days where it's like kind of cloudy all day and rainy all day, on and off. Not like a one quick bam storm, but like it's just been raining and raining and raining. That's usually this situation. Again, in a very textbook situation. Weather's very complicated. Zoom the map out to here and try to figure out what's going on in all these different situations. We can say, ideally, a cold front's like this. Ideally, a warm front's like this. Ideally, a low pressure system's like this. But by the time you throw in all the other variables that are difficult to understand, transitions from land to water, mountain barriers, it's an extremely complicated science that we're trying to strip down to like, what are the bare bones here? So this is bare bones textbook, exactly how a warm front should work. So if we're in map view, if we're like looking at this, what should we have with what you see with storms? Let's see if I can pause this one. We'll refresh. Just stop the animation here. All right, so I would estimate, these runs of fronts, that's your cold front stuff, and your low is probably right about in here, and then this last bunch of mess right here would be the warm front stuff. In other words, what does it look like in map view? Well, you're going to have a low, you're going to have your mid-latitude cyclone, just like we drew right here. These always look this way. Sometimes you get lucky and a question is just as simple as they'll give you these fronts like rearranged or flip backwards or doing whatever. A mid-latitude cyclone always looks this way. They always travel around in a counterclockwise direction. They can't go the other way. It doesn't work. So the drawings will be with the teeth pointed towards where it's going towards, just like that. It's your very typical mid-latitude cyclone. Textbook mid-latitude cyclone. With the two ends attached to the low. And looking like that. So where does the rain happen? Rain you tend to do in green on a map. You're going to have thunderstorms right on top of the cold front because, again, that's where that cold air lifts this warmer air up off the map and dumps its moisture right back down up very quickly. You're going to have rain out ahead of the warm front in kind of a larger band because it's just kind of generically slowly raining out ahead of that. And then around the low itself will tend to be rainy because, again, the rising air as it goes towards the low and comes on up. Okay. That's multiple weeks worth of earth science work crammed into 10 to 15 minute videos. So again, I have confidence that you're going to pass, but I just want to make sure that you see at least a little bit of exposure to these other things. Why is the warm, moist air rising at the frontal boundary? I'd say it's because that cold air is moving forward and like shoving its way underneath, making that warm air rise up. The cold front is displacing it on the surface. One process that causes clouds to form in the rising air, multiple correct answers. When air rises, it expands and cools, will work. When it cools, it could reach the dew point, could work. That when it hits the dew point, it's saturated, 100% relative humidity, and clouds form. Any of the stuff from that list that we wrote all works. Central Canada was a geographic source region for the CP air mass shown in the cross section. Identify the most likely geographic source region for the MT is going to be the Gulf of Mexico. That's wet, warm air comes from wet, warm places. So that would be Gulf of Mexico. All right. More to come. I probably am going to stop for today, but I'll do some stuff with station models, and I'll just look for other gaps that we had and do a few more videos tomorrow. Thanks for tuning in. Good luck.